name is Daniel Fedorov, and welcome to my presentation on designing better products, a project I completed for ME 3210 with Dr. Hassan Rashidi. So the goal for this project was to identify 5 key processes that I learned throughout the course that I found particularly interesting. Now, I have a particular fascination with mechanical design, so the 5 processes I have outlined here fall under the general umbrella of the mechanical design process. So let's take a look at these 5 processes. First, in order of how these would be completed during the design process would be problem definition, then concept generation, then concept selection, product prototyping, and finally performance evaluation. First, let's take a look at problem definition. So on a broad sense, this is how do we define what problem we need to solve. First, of course, it's very important to identify customer needs through surveys, interviews, and observations, and answer the question, is the problem really worth solving? It's important to identify gaps in existing solutions or products, and also get a general outline on the constraints you'll be working with throughout the project, whether they're economic, environmental, or technical. And as you're doing this, it's very important to consistently be collecting customer feedback. Now, some of the tools we could use for this would be affinity diagrams, stakeholder interviews, and surveys. The next step in problem definition would be establishing requirements. It's very important to develop clear and measurable engineering specifications during the problem definition phase. To do this, we can create functional requirements and also identify key design standards, regulations, and compliance needs that we need to meet. Some of the tools we can use to achieve this would be a house of quality, a quality function deployment, or specification tables. Now, it's very important to note that during the problem definition phase, outlining specific engineering requirements may be quite difficult. Therefore, it's important to get a broad understanding of what needs to be achieved, and more specific engineering specifications with hard, tangible numbers attached to them will be achieved later in the design process. Next, a very important step of problem definition is to plan the project that you're going to tackle. With a clear project scope and deliverables, any task becomes a lot more manageable. Timeline with established milestones and roles and responsibilities for all team members is absolutely essential. Otherwise, a ton of time will be wasted as team members are unsure of what to work on or work inefficiently on tasks that are being done in parallel. A couple of very helpful tools to achieve this would be a Gantt chart as shown here, or a work breakdown structure, or a program evaluation review. Now there's plenty more project planning tools available, and these are just some of the common ones that are used in mechanical engineering. A little bit more here on the Gantt chart, as it's probably one of the most commonly used tools. It's a very elegant way of expressing which tasks can be done in parallel, while which tasks rely on the completion of others in order to be started. So that's why it's a very, very important tool for using early in a project to establish which tasks have to be completed before others, while also analyzing what can be done in parallel to better use team members' time. Next up would be concept creation. So this is sitting down and getting to the brass tacks of brainstorming ideas to tackle the problem you're solving. Now, it's very important to consider that there's no bad ideas during this process. It's important also to promote quantity over quality of ideas, as quality of ideas will be, as the more ideas you have, the easier it is to find quality ideas in the mix. Encourage risk and unconventional approaches, and it's also important to build upon the ideas of others. Concept creation should be a time of no judgment and quickly creating as many ideas as possible. Some common tools that are used for this are morphological charts, mind mapping, analogies in design, scamper technique, and group brainstorming. And here to the left, we have a morphological chart that I created for ME 2110, which was a class I took 2 years ago, as we tried to design a robot to complete certain tasks. So as you can see, there are plenty of ideas. We're not so much concerned with the quality of the idea. We just want to get as many down on paper as we can to then later go through and select which ones will be best for our approach. Next, we want to explore the design alternatives. So here, it's important to narrow down options from the ideation stage discussed previously. We want to consider the design modularity, the scalability, its functionality, explore materials, manufacturing techniques, and assembly methods on a broad scale. Finally, you want to ask yourself, how do the aesthetics, ergonomics, and user experience impact the design? For exploring these design alternatives, as I mentioned previously, you can use a feasibility analysis, technological readiness assessment, design matrix or Pew's method, and a risk table. And here we have an example of a decision matrix that can be used to evaluate the many design approaches or options we created earlier and start whittling them down into a select handful of feasible designs that we can use for our final product. And finally, a very important part of concept creation is the organization and documentation of this entire process. Organization is key to effective concept creation. You have to make sure you make ideas easily accessible for reference later in the design process. Many times, someone will come up with a great idea early on in the design process, and later on someone will ask, what was that idea? How can we fix this issue we're currently having? And if it wasn't written down, everyone will forget it. So it's very important. Every idea should be marked down, sketched, cataloged in some way to ensure it can be referenced back later. Some good tools for this would be just rough CAD sketching, idea logging, and function trees, as you see here. Now, function tree, again, is a great way of just breaking down the functions that a potential prototype or idea can have in order to achieve the final wanted result. Now, the next of the 5 processes we'll be analyzing in the mechanical engineering design process is concept selection. So here, first, we want to define the evaluation criteria. We want to see how we're going to be taking the design ideas that we came up with and whittling them down into just a small handful to make our final product. So first, we want to establish key performance metrics for the design, such as functionality, cost effectiveness, sustainability, and manufacturability. And an important concept in concept selection is that data and hard requirements separate this stage from the previous. So previously in concept generation, we were working more with nebulous concepts, just trying to come up with as many ideas as possible. Now, we want to get hard data to start to choose from those design concepts. Now, some tools for this are the Kano model, designed for X, so it could be designed for manufacturability, cost effectiveness, sustainability, and the house of quality, again, for helping choose between different requirements. And here you can see the Kano model of customer satisfaction, which shows a relationship between customer satisfaction and the performance of a product. The next step in concept selection is choosing a design. So here we need detailed and structured evaluation methods on a very small number of ideas in order to pick the best one. We're going to use objective scoring methods that have to be data-based. We need to make sure we also keep open communication with the customer base during this time of choosing the final design, as this will reflect more positively to ensure that the customers are always part of the design process. And now is the time to commit to an idea. So in order to do this, we'll use a Pew matrix, a weighted scoring matrix, a mishap probability or severity analysis, and pairwise comparison. Now, it's important to perform a risk severity analysis to ensure that we have a very good understanding of where the potential pitfalls are in the design we're choosing, the risks associated with those pitfalls, and the potential costs or time associated if those risks were to come to fruition. And finally, we have to refine the chosen idea. Once an idea is chosen, it's time to commit. Ensure that all team members have a clear vision of the product and exact problem it aims to solve. Or else, what if the team members don't have alignment on the final vision of the product? It will be very, very ineffective and hard to design. Additionally, you can perform an early stage FMEA analysis, failure mode effect analysis that is. Where might the design fail and how often? And identify potential problem areas in the design as early as possible. To do this, again, we can use a failure mode effect analysis, as shown on the left. And also we can use risk assessment matrix, and now would be a great time to start CAD modeling and sketching and being in much more detail about how this product will come to life. Now next is arguably my favorite step, and it's product prototyping. So first we have to plan the prototype. We have to identify key features that the prototype must have and also choose how the prototype will be made. This is important as we have to select and weigh processes for the late stage prototypes and the early stage prototypes. Selecting materials also have to match the final product to meet the specifications. Use the prototype to evaluate how the final product will perform. So we want to make sure the prototypes are as close to the final product as possible, while considering spatial and functional constraints. So here on the right, we have a materials selection chart that can be used to quickly and easily pick a material that can be used for a prototype. So the tools used for prototype planning would be CAD modeling or sketching, rapid prototyping, design of experiments, and also various material selection softwares that make it very easy to pick a material. Finally, we have building the prototype. Now, building a prototype can be a whole slide presentation in and of itself, but quickly we can choose from many manufacturing processes to build this prototype. Now, the main question we want to ask is, how does the manufacturing process impact performance of the prototype, and how will this performance differ from the final product? And again, for later prototypes, we want to make sure we use a process to manufacture as close to the original process. Here on the screen, we have two images of potential manufacturing methods you can use. We can use CNC if we want to make the prototype out of metal, and now resin printing is an emerging technology that has become fantastic for rapid prototyping, where we get prototypes with very, very good quality and great material properties. Again, some tools for this that we can use would be CAD modeling, sketching, CNC machining, 3D printing, and breadboarding for electronics. Now, the last step in this mechanical design process would be performance evaluation. We want to do this, we need to collect data to perform the evaluation on. We need to collect performance data on the final prototype against the engineering specifications we created earlier. And if for some reason the prototype is not performing as expected, we should perform RCA, or root cause analysis, to identify where the pitfalls in the design are. Finally, the manufacturability of the prototype should be evaluated while considering the tolerance stack-up and the cost feasibility. And we also should verify the results that the prototype performs correctly through repeatable experiments. Now, an interesting analysis here on the cost feasibility of a prototype and therefore a final product is this cost analysis with steel machining. And we can see how as our tolerance increases, our cost increases exponentially. So this shows that cost feasibility is a very, very important metric to consider while still in the late prototyping phase. Some tools for this process of performance data collection would be tolerance analysis, design of experiments, statistical analysis, and root cause analysis. Now, finally, we've come to design optimization. Now we have the final prototype in our hands, we've collected plenty of data, and now we need to analyze and optimize the design we have. So we should perform detailed analysis on all failures, and we need to answer the following. Is the product still worth manufacturing? Is it sustainable? Is the product maintainable? These questions are very important to answer now, because the design process only accounts for 5 to 15% of the product cost. We should optimize the product before it's put into manufacturing. On the right, we have a great visual of this. As you can see, the design is only a very, very small sliver of the overall cost associated with creating this product. Again, if the design that's created is not easy to manufacture, or it's ineffective to manufacture, this could cause huge extra costs on the final product and therefore make the product way more expensive than originally intended. Thank you very much. I appreciate you listening to this presentation. Thank you.